Here in chapter 6.2, we're going to explore exponential functions and their derivatives. So let's remind ourselves first what exponential functions are. When we have a whole number as an exponent, we think of that as a repeated multiplication. For instance, 2 to the power of 5 is just 2 times itself 5 times. So you can perform the operation that way. In this case, 2 times itself 5 times gives me 32. If we have a rational function or a rational number as an exponent, what does that mean? So for instance, if I've got 1.5 raised to the 0.4 power. Well, any rational number can always be expressed as a fraction. And so really this boils down to thinking of 0.4 as the fraction 2 over 5. And now we have a way of evaluating this using radicals. So this would be the same as the fifth root of 1.5 squared. So anytime we have a rational exponent, we always have a way of evaluating it using a radical. Now the question is, what if we have an irrational number in the exponent? For instance, here, square root of 2 is irrational, but it can be approximated by a rational number. Because any rational number we can evaluate the exponent with any rational number. We'll use this approximation of an irrational number with a rational number to find its exponent. So in this case, the square root of 2 is really an example where if we were to try and write its decimal approximation, you'd get this non-repeating, non-terminating decimal, 1.41421, and so on. Okay, so this would keep going. But because this is an ongoing sequence of decimals, we can think of this as the limit of the sequence of rational exponents. Say we have, 3 to the power of 1, 3 to the power of 1.4, 3 to the power of 1.41, 3 to the power of 1.414, 3 to the power of 1.4142, 3 to the power of 1.41421, and so on. This sequence would get progressively closer to the actual value of 3 raised to the square root of 2 power. So in a sense, we're defining the exponent b to the power of x as the limit as r approaches x of b to the power of r, where r is a rational number. So let's just quickly remind ourselves some basics about exponential functions. Here we're looking at the family of exponential functions of the form b to the power of x. We can kind of see here in the graph to the right that depending on the base, right, b being the base, our graph can take on a variety of different shapes. Notice that the higher the base is, the more steeply the graph rises. For instance, 10 to the power of x compared with 4 to the power of x, 2 to the power of x, and 1.5 to the power of x are getting less steep as the base decreases. And then 1 to the power of x, notice, is actually a constant function, because 1 raised to any power always stays 1. And then when we have bases that are less than 1, for instance 1/2 or 1/4, we get this decreasing shape. And again, the same idea applies, that the bigger the exponent, or I should say that the bigger the base, the more steeply that curve is going to rise. So we have this basic rule comparing the shapes of these exponential graphs that with a base between 0 and 1, it's a decreasing exponential function. With a base equal to 1, it's a constant function, and then with a base that's greater than 1, we get an increasing exponential graph. So this is one way to characterize it. Here I would consider this maybe growth function exhibiting exponential growth. This one's decreasing, so we would consider this a decay function exhibiting exponential decay. On the other hand, this one in the middle would just be a constant function. Here we can compare the different growth rates of exponential functions versus power functions. So like 2 to the power of x compared with x to the power of 2. Notice that if we're just looking at the graph here, that the exponential function here is going to be a little bit different shape than the parabola x squared. It might appear from, up close that they're both kind of increasing, curving upwards here. But really, what happens is the exponential function 2 to the power of x is going to start to blow up, and it's going to get very large very rapidly. Versus the x squared graph is going to be much smaller in the long run. So here on this scales from 0 to 4, you can kind of see, they kind of go back and forth. One's bigger than the other, and then eventually exponential gets bigger. But then here in the larger scale, you can kind of see how the exponential function starts to get much larger than the parabola. Here are some basic laws of exponents. Some x plus y in the power can be split up into two separate products, b to the x times b to the y. B to the x minus y is equal to b to the x over b to the y. B to the x to the y is equal to b to the power of x times y. And then ab to the power of x is equal to a to the x times b to the x. And these basic laws are ones that we can use later on to establish some facts about exponential functions and logarithms later on. And beside that, it also here is establishing that when the base is greater than 0, we have an increasing function, and when the base is less than 0, we have a decreasing function. Here we can remind ourselves just of that picture that we had earlier. When we have the base is greater than 1, we get a graph that looks like this. We see that as x goes to infinity, the graph is going to go to infinity, and as x goes to negative infinity, the graph is going to approach 0. So we've got this horizontal asymptote at 0. On the other hand, if b is less than 1, then it'll be the opposite direction, where it's now decreasing. So here b is greater than 1. Here b is between 0 and 1. So let's just look at an example here where I want to find the limit as x approaches infinity of 2 to the power of negative x minus 1. So 2 to the power of negative x would be in this case, something that we could perhaps write a different way. 2 to the power of negative x, that's really 1 over 2 to the power of x. So we can think of that as 1/2 to the power of x. And now as x goes to infinity, because this base is less than 1, this is going to go to 0. So we're left with 0 minus 1, or just negative 1. So what would the graph of this function look like? Well, it would be the graph of 1/2 to the power of x, and then shifted down 1 unit. So it's like our horizontal asymptote gets shifted down 1 unit. And so we get this decreasing exponential function that tends towards negative 1 as it goes to the right. And before we can find the derivative of b to the power of x, let's just see what happens when we try and write out the definition of the derivative. So we know f prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x over h, which in this case will be b to the power of x plus h minus b to the power of x over h. I can use the property of exponential functions that says b to the power of x plus h is b to the power of x times b to the power of h. And then I can factor out a b to the power of x from those two terms. So I have b to the power of x and then b to the power of h minus 1 over h. Since b to the power of x here does not depend on h, that can be separated from the limit. And so in order to find the derivative here, we see it's some value here. Multiplied by b to the power of x. So what we've kind of seen here is that the derivative of b to the x is going to be some constant that would be found by evaluating this limit times b to the x. So we have to figure out what this constant is going to be, what this limit actually approaches. So it's, we'll say here it's some constant times b to the x. So what is c? And actually we should notice that here c really does depend on b, so it's really kind of like a function of b. And this is essentially how we're going to be defining the number e. So here, when we're defining what the number e is, it'll be a special number that has this property that when I take the limit as h approaches 0 of e to the h minus 1 over h, we get 1. So it's like the derivative of e to the x, which we've shown in the previous slide, is equal to e to the x times the limit as h approaches 0 of e to the h minus 1 over h. If this is going to equal to 1, then the derivative of e to the x is just equal to e to the x times 1. So really, e is this special number whose derivative is equal to itself. The derivative of e to the x is equal to e to the x. And so by defining e this way, we have this special exponential function where e is this particular number. We'll also see e can be thought of in other ways, but this will be one way that will be particularly useful for us.